Okay, let's start adding components to our breadboard. I want to talk about resistors, and I want to talk about LEDs, and I want to talk about why I can only get 2 out of these LEDs hooked up in series to ever turn on. And it's not because the other 3 are broken. Let's start with resistors. Start by grabbing a resistor, and for now it doesn't matter which one, because the first thing we're going to do is measure its resistance. And holy smokes, electronics components are small, so use a pair of tweezers if you're finding yourself aggravated trying to pick them up. Okay, what is a resistor? Well, think about electricity and think about it like a stream of water. Imagine this stream of water flowing downhill from a positive voltage to a negative. And now imagine rocks in the stream. The more rocks there are, the more the water is going to bump into the rocks before it can get around them. And if you put enough rocks in the stream, you could essentially dam up the stream and nearly stop the flow. Well, resistors function in a similar way. They resist the flow of electricity in a circuit, and if the resistance is high enough, they can stop the flow. And in electrical terms, the flow of electrons is called the current. And we could look up how much this resistor resists the flow of electrical current by matching these 5 colored stripes to a resistor identification chart, or we could just measure the actual resistance on our multimeter. So let's do that. Switch to ohms, because ohms is the unit of resistance, and then take your probes and put 1 probe on either side of the resistor. And here we can see that this is a 220 ohm resistor. And if we flip it around so that the probes are touching the opposite legs, we can see absolutely no difference. Another 220 ohms. Resistors don't have a direction. They just resist the flow, whichever way it's flowing through. Now, I don't particularly like measuring components in my hands because if there's a bit of water on my hands, there is a path of electricity across the surface of my fingers that could change my measurements. So sometimes I just use the breadboard as a stand. I'm not thinking about connecting it to any other components at this point. I'm just trying to put the component somewhere so as to not touch it with my fingers. And even with this quick test, I can see a difference. Here on the breadboard, I'm measuring 220.4 or 0.5 ohms of resistance, and held in my hands, I was getting 220.3. That little difference was consistent, and if nothing else, can serve as a reminder that your body can become a path for electricity to flow. Okay, now let's use the resistor. Plug 1 leg of it into your positive rail, and put the other leg somewhere in the middle of the breadboard. Here I got it into row 6. Then grab a red LED and notice this important detail that one of the legs is longer than the other. The long leg is the anode, and it's got to connect to the positive side of your circuit. The short leg is the cathode, and it has to connect to the negative side of your circuit. And on the breadboard, the positive side of my circuit runs down the positive rail, up and over the resistor, and it fills up row 6 here. So I'm going to put the anode, the long leg, into row 6, and the cathode, the short leg, into row 7. And now I'm imagining that my circuit extends to here. And then if I put a jumper wire into row 7 somewhere and connect the other end of the jumper to the negative rail, I will close the circuit. Okay, now if I look past the swirling jumper cables and the bent legs of the resistor, I've got a couple important concepts here. I have a voltage source, which is then passing through a resistor, and then from there through an LED, and then from there back to ground. And a great way to represent important concepts is with a schematic, sometimes called a circuit diagram. It clears away all the clutter, leaving you with just the ideas. And for us, the ideas were a voltage source, some wires, a resistor, an LED, and then more wires that return us to ground. And as a beginner, I highly recommend that you start making your own schematics each step of the way. I'm using LT Spice to draw my schematics. It's simple and free, and I recommend that you do the same. When working on a breadboard for the first time, it can be a legitimate question which of these details matter. Is it critical that we plugged our resistor into row 6 and our LED from row 6 into row 7? Does it matter where we plug the far end of our wire onto the ground rail? The schematic helps clarify that the answer to all these questions is no. There are thousands of ways I could hook up this circuit on this breadboard, but all of those differences don't matter so long as I have a voltage source, a resistor, an LED, and a return to ground. each of those thousands of circuits would be equivalent. Okay, now let's make an equivalent circuit that makes it just a little bit easier to test our voltages at different spots on this circuit. Let's plug our wire that used to go to ground here onto row 12, and then get another wire that goes from row 12 over to ground, and then get a header pin in between those two wires on row 12. Our circuit is still equivalent to our schematic. It just has a header pin here, a sort of exposed wire, so that we can measure our voltage just after the LED. So let's do some measuring. Turn your multimeter onto volts DC mode and get the negative probe of your multimeter situated on that header pin over on your negative rail. And get the positive probe on your positive rail, either on the header pin or on the leg of the resistor. And you should see about 5 volts. Write down the number that you get out to 3 decimal places. Then move your positive probe to the other leg of the resistor and notice the voltage drop. I dropped down to 2.077 volts. Write down the number that you get. Then move your positive probe to the far side of your LED, the cathode, the negative side of the LED, and notice the voltage drops again down to 4.5 millivolts. And notice that our units change to be 1/1000th of a volt. Now move your positive probe to the header pin and see the voltage drop again, now down to 0.5 millivolts. And one more time to your final header pin, where we can measure even this difference of 0.1 millivolts. And if you touch the two probes together, you should see them drop down to 0.0 millivolts. Okay, let's get these voltages onto our schematic to make them clear. And let's start with 5.008 volts. And what this really means is that there is a difference, and you can think of this difference as pressure pushing on water through a pipe, pushing electrons through the wire. And this difference is relative to the end of the circuit, which we're going to think of as 0 or ground. And so the start of our circuit is positive 5.008 volts. And at the risk of too many analogies, it can also be helpful to think about this positive voltage as altitude, height up a mountain. You've got the ground, this is 0 volts, and then you have the mountain, and our mountain is 5.008 volts high. And if we take an electron, a little stone, and we roll it down the hill, it will roll all the way down the hill to the bottom, and when it gets to the bottom, it will stop. There's no more difference between the height of the stone and the height of the ground. It has no potential to go any further. Okay, our next measurement was 2.077 volts, and that was taken just after this resistor. Our voltage has dropped by more than half. We are more than halfway down the mountain. Our next measurement was after the LED, and our voltage dropped to 0.0045 volts. We're basically down at the ground now, but even down here, there is a measurable difference at 0.0005 volts, and then at 0.0001 volts as we get closer and closer to the end of our circuit, suggesting that even the wire itself has some resistance, and the further along we are on it, the more our voltage is going to drop. Okay, with this ability to measure voltage drops, we're a little closer to understanding why we can only get 2 of these LEDs in series to turn on. But there's more to this story, and it's going to take additional tools to understand it. So next up, we're going to say hi to Ohm's law and show how powerful and useful a tool it is when trying to understand simple circuits.